Hi, my name's Aisling. I've been working on Project 2004 with Nathan and Stefan. We've been working with Cinica in Bologna, which is home to the Marconi 100 supercomputer. The Examon framework is used for monitoring time series data on the Marconi 100. This data is used for analysing the performance and efficiency of the clusters and can be used to dictate job scheduling and resource management. The data can also be used for building machine learning tools to detect anomalies on the clusters. This is the architecture of the Examon framework, beginning with the sensors collecting data on the bottom from the nodes of the supercomputer, and then the MQTT brokers direct this data to the appropriate locations within data storage. Applications can then be built connected to this data storage. My project was based on integrating a data visualization software called Redash into this current monitoring framework so that Redash could be used to model this time series data. Redash is particularly useful for visualization as it supports many different databases and integrations, as well as allowing querying through the query language native to the data source. The Examon framework contains its own NoSQL database called KairosDB. With that, we use its own built-in Examon query language. To implement Redash into the Examon framework, it was necessary to alter Redash such that it could understand and use the KairosDB data source. To do this, we needed to create a base query runner in Redash in Python for the KairosDB. This file that would instruct Redash how the KairosDB is to be accessed. Once this is done, the Redash software can be used on top of the monitoring framework Examon to visualize the data.
Welcome to this presentation on anomaly detection in high-performance computing systems as part of the 2020 PRACE Summer of HPC program. This project concerns the Marconi 100 supercomputer of Cinica in Italy. With peak performance of 32 petaflops, this powerful machine is one of the fastest in Europe. The 980 nodes, with RAM of 256 GB per node, all contribute to Marconi 100's speed of computation. These powerful HPC systems are used to accelerate scientific research. With such complex systems comes failures in their function, the causes of which are numerous, for example, imperfections in software, hardware malfunctions, or overheating components. In order to better understand our HPC systems and their weaknesses, we must monitor their behavior and detect anomalies in system operation. Marconi 100 can be investigated through use of a tailored query language called Examon Query Language. The describe command reveals the 1,500 metrics which are available for monitoring. These metrics can include, for example, system power or the power state, and this data is collected for further analysis. One exemplary metric is the temperature of a particular CPU. This particular metric is measured by the Confluent Pub plugin and relates to a specific node described in the table of the Galileo cluster of Marconi 100. The data is stamped with the time of collection, called the timestamp, and displayed as a table. Much more useful would be to visualize this data in graphical format to observe how the CPU temperature varies over a given time frame. The time series plot allows us to see that over a given 2-day time period, there are large fluctuations in temperature of this particular CPU. This could be due to inefficient cooling or differences in air temperature. It's desirable to monitor these metrics in a more user-friendly fashion. Grafana is a web application which provides interactive dashboards such as this displayed. An ongoing project is to display the metrics of Marconi 100 in a Grafana dashboard so that these can be monitored in real time. These metrics will be system power, GPU and CPU temperature, and drain status, and give the user insight into the behavior of the Marconi 100 system. Beyond an interactive dashboard, patterns in data and anomalies are difficult to realize with the human eye. Future work in anomaly detection will use machine learning techniques to recognize these patterns. Further, humans are less capable of determining anomalies according to particular criteria compared to machines. These machine learning techniques will allow for automated and uniform anomaly detection, which will ultimately provide useful insight into HPC behavior.
Hello everyone, my name is Stefan Popov, and during this summer I was participating in the great Summer of the HPC program at the Cineca Consortium in Bologna, Italy. My task during this project was to transfer historical supercomputer data from their current platform into Delta Lake format, and this is what I'm going to talk about next. So, Cineca has implemented a monitoring framework that records data about its supercomputers. This framework is called Examon, and it records various attributes about the supercomputers, such as environmental data, power management data, information from the job scheduler, hardware usage data, etc. Here we can see the Examon architecture. The physical sensors record the data in time series databases through the MQTT protocol, and from there we can use any processing engine to query the data and do analytics. For this project, my task was to store a snapshot of the data from the Examon framework related to the state of the new Marconi 100 cluster Cineca into the Delta Lake format. So what is Delta Lake? Simply put, it's a storage package within Apache Spark that complements its functionality and offers many great features. So when I talk about working with Delta Lake, I mean I'm executing Spark code. The most important feature of Delta Lake is that it guarantees data integrity, i.e. each data transaction is acidic, that is, it is atomic, consistent, isolated, and durable. Data Lake offers both schema enforcement and evolution, thus preventing data corruption and enables seamless schema modification. It works with the column-oriented Apache Parquet format, saving a lot of storage spaces for long tables, which is the case with our project. Delta Lake is fully compatible with the most popular cloud storage solutions such as Hadoop, Microsoft Azure, and Amazon's S3 system. Executing Apache Spark on a cluster of computers is no easy task and requires quite some configuration. Luckily, there exists a Python package called Spark HPC, which automates a lot of the work for us. It schedules the execution of my Spark code to the Slurm scheduler, enables utilization of the resources of the Galileo supercomputer where I ran my experiments. To accomplish my task, I had written a Jupyter notebook which reads the data from the Examon servers, reads into the Spark data frames, and saves them into Delta Lake format.